a pleasure for me to be here with you today and share my experience and also my, hobby that I've been carrying out for a while now in the world of reinforcement learning. So you already went through a very, high level outline of what we are gonna see today. And yeah, let's see a very quick summary. I'll start with a few words about myself, so who I am and what's my background. And then we are going to start from a little overview of RL, reinforcement learning in practice. So some definitions to give you context, and then the goals and solution methods adopted in the field. Some, mentioning a few advanced techniques, challenges typical of this domain, some in industry applications, and in the same, topic, I'm going to share a few resources that you may find very useful if you want to approach the field. Then I'm going to share the Umbra project. That is something that I've been working now more than a year. It's something that you will see. It covers both reinforcement learning environments, training deep reinforcement learning agents, and also a tournament platform, that we are building to foster advance in research and experimentation in the domain, allowing people to compete with their trained agents. Then we will be watching a trained DeepRL agent playing one of the games that are made available by DIAMBRA. In particular, we are going to watch today Street Fighter 3, and we will take a look at it, hoping it will be able to play very well. Usually, it is able to complete the game, so we will see. And then, both during those gameplays as well as afterwards, we will have time for question and answers. And at the same time, we will be also code very first, simple usages of our environments, so that you can see how easy it is to get started. Okay, so first of all, a few words about me. Alessandro Palmas. I'm the R&D lead engineer in Nuriana Technologies. It's a company in the aerospace and defense field. We are located in Cagliari. And my background, I'm an aerospace engineer. So everything for me started from that field. But I was also very interested in the computer science in general. So after graduation and after starting to work in the software domain, like building complex scientific applications in the field of computational fluid dynamics and similar things, I got really interested in machine learning as a general topic at first. And so I started, putting some effort in learning it in my spare time. I approached it mainly to different fields. So computer vision, that was the first one. And I've been lucky enough to have the chance to mix this passion with my day-to-day job, being in charge of R&D efforts. Company allows you to experiment a little bit, to create space for experimentation of these new technologies in research projects. And this is what I did. If you go on LinkedIn and find myself, I'm more than happy to expand my network, connecting with people that share this common interest in these fields. And you would be able to see how, for example, we applied computer vision in the domain of flying drones in order to enable autonomous navigation, for example. So that was one of my main interests in the machine learning world. Right after that, actually, the main one was reinforcement learning. These images I put here are showing, for those of you who are familiar with the context, there is AlphaGo were from DeepMind, and also OpenAI 5. So two great milestones in the world of reinforcement learning, in which two great AI labs, DeepMind and OpenAI, they were able to achieve results that demonstrated the great potential reinforcement learning has. And so, that was for me, a moment in which I decided I wanted to really put some very important effort in this world. And so, in particular, in this specific subdomain of machine learning. And this is where, I decided to create the Umbra. I will tell you more about it later. And yeah, but this is more or less my trajectory up to today. So let's start from a very classical first step. When you approach machine learning, you are usually presented with something like that, like what you see on my screen. The entire world of machine learning is typically divided in unsupervised, supervised, and reinforcement learning. And so, of course, you surely know unsupervised tasks, are usually divided by clustering and dimensionality reduction, while supervised learning is, composed by classification and regression. So you find different problems in these two different subdomains. And reinforcement learning is a third sphere, let's say. Now, this is just one possible clustering of the machine learning world, but for example, reinforcement learning can also be seen as a generalization of the supervised one. So it's not like very fixed grouping, and so it's very common to find in reinforcement learning. To learn reinforcement learning, you need to be familiar with supervised, with unsupervised. You use methods you learn in those fields, so it's some way related as well as dependent on them. At the same time, it's kind of peculiar in the sense that reinforcement learning has a slightly different formulation than the others, and it's pretty, specific. And it usually is defined by means of these or similar schemes to this one, the one that you see on the screen now. So you have on one side, you have an agent or an algorithm, let's say, and this agent needs to interact with the world. That is usually, referred also as an environment. He interacts with this environment in sending what we call actions, and receiving from the environment observation and usually also a reward. Now, this is the standard definition of a typical reinforcement learning problem. Maybe it's worth mentioning that sometimes you may find the term state instead of an observation, and the reward is not always there, but usually in the typical formulation this is the case. Now, using state instead of observation is not always correct, because state is what describes the environment situation, while observation is typically a subset of the state space. And that the observation represent what you are able to see about the environment state. And this is what the agent or the algorithm is using to decide the next action. So training an agent in this context, so training a model, means to find something that we will call policy, something that, given an observation, is able to select an optimal action in order to optimize a reward. Now, this is a loop, as you can understand from the scheme. And so these actions needs to be, of course, sequences. So you need to select multiple actions in sequence in order to optimize at the end your reward. There are multiple aspects of reinforcement learning that define different contexts. Like, for example, one typical difference is continuous tasks opposed to episodic tasks. Now, as the term clearly states, episodic tasks are tasks where you have a clear, start of the episode and a clear terminal state, so end of the episode. In our case today, we're going to focus only on episodic tasks, and this is sometimes even easier when first approaching a reinforcement learning. So, having described this scheme from a high level, we can dive into a little bit of code to understand how this is translated in a typical snippet, code snippet, where you where you have the goal of creating this interaction. Now, what you see here is something that we are going to use later, and is the very simple way in which you can interact with our environments. Because in DIAMBRA, one of our efforts has been to create a package of reinforcement learning environments, reinforcement learning problems that are made by using popular video games, in particular fighting games. I'll talk about it more later, but this snippet tells you how easily it is to start. So first of all, it's of course a Python interfaced environment. So once you have it installed in your system, you can just import the Umbra Arena. This is the name of our environments. Very simple settings, like in particular, two of them are mandatory. So the first one is the game ID, specifying which game you want to play. The second one is the path in your system where your ROMs files, so your games, are located. Apart from that, you just create the environment, specifying, with this function, the Umbra Arena.make, the name of your environment and passing the settings dictionary. Then you reset the environment. This is a typical approach in this field. And by the way, this interface is what is called OpenAI Gym interface. This is a standard that is typically used for environments in the reinforcement learning domain. So the first thing you have to do before starting the interaction is to reset. And this operation just brings you to the starting point of the episode. So this reset operation gives you the observation, the first observation of the starting moment of the episode. And after that, you start your loop of interaction. As you can see, there is a while here, and you'll start interacting with the environment in this way. First, you use your observation. So a trained agent would use the observation to select an action. In this case, instead, I'm just randomly sampling the environment action space. So I'm selecting an action among those available in a random way, and I'm sending that action to the environment in the next step. As you can see on the right, there is environment and .step actions. So I'm sending those actions, the environment is executing them, and as a result, we obtain an observation. So the next observation, a reward that is a measure of how good or how bad you are doing in that environment. And then a done condition, typical of episodic tasks, that tells you when the task has reached the terminal state. And finally, a dictionary, the info dictionary, that gives you some information for logging or debugging. And this loop goes on and on for a long time until you reach the terminal state. Once you reach the terminal state, your episode is done, and you just break the loop, and that's it. So let's talk about the reward very quickly. In our case, for example, the reward, so we will be talking about video games, in particular fighting video games, and the default reward that we have and we provide is a measure of the damage, so the health bar, how it behaves. So if you are able to cause damage to the opponent, your health will be positive. So you will receive a positive reward for hitting the opponent. You will receive a negative reward for if you are hit by the opponent. Now, and this is proportional to the amount of health you win or lose, and this is our reward function. You will see it in action in our execution of our trained agent, and this is how it works. So the goal for us in our environments is to train an agent that is able to send actions. It means, in our case, to press the right buttons in the gamepad so that the reward is maximized. So you're able to hit the opponent while avoiding being hit by him. In our case, the observation, this is a typical example of the observation space. And for us, it's a composition of, first of all, pixels, so the screen, and some numerical values. Now, to be clear here, when you play as a human, you play these games, the information you use to select your actions is the screen. So you keep looking at the screen and decide the next action based on what you see on the screen. So in principle, the pixels should be enough. Now, and you can use, train your agents only using those pixels. But we also provided some numerical values like those represented here on the right. For example, numbers about health values of your characters as well as the opponent ones, number of wins, if you are on the left or on the right, which character you are using and you are facing. So these things. Now, these are just a few numerical values, and it's important to know that these are all aspects that you can retrieve from the screen pixels. So there are no hidden values. There is no way you can cheat about it. All these things we provide as numerical values, they are already there. So everyone looking at the screen can know that. For the actions, so this is what is called the action space. So which type of actions you have access to. And as you can see, we provide 4 different options. The first, grouping is between discrete, the discrete action space, and multi-discrete action space. So the discrete action space is an action space that is made of a single set in which all the actions are listed. So without distinction between move and attack actions. So all the actions are there, and you can select only one action in every step. So you can either select your move action or your attack action. In the multi-discrete, instead, you are given 2 different sets, move actions and attack actions separately. So you can select move and an attack action in each step. So you are able to send 2 actions per step. The second difference that creates 4 different action spaces is if you want to use attack actions, attack buttons combinations or not. So this is, in some games you can press 2 different buttons at the same time for the attack, and the result is a different outcome if with what you are able to achieve just pressing one single button. We added this option in order to limit the number of action, and so in some games it's more than enough to just press single buttons without allowing to press multiple buttons together. Of course, this comes with limitations. For example, in Dead or Alive, if you press, the only way in which you can counter a long sequence of catches by the opponent is by pressing 3 buttons altogether. And if you are selecting, an action space without the attack buttons combination, you are not able to interrupt this. So it's always a trade-off between higher space, in this case the action space, with limitations that the game has if you don't use those actions. Now, coming back to the goal of reinforcement learning is finding the optimal policy. Finding the optimal policy means that you receive some observation. As you can see here, in our case, the observation is made of frames and also numerical values listed in the bottom part at the center of the image. And you need to use this to select your next action. And now the goal here is to find an optimal way to select the next action so that at the end of the day, your cumulative reward, so the amount of reward you collect during your episode, is maximum. This is the goal of reinforcement learning. How to do that? Well, there is an entire, this is the key point and problem of reinforcement learning. And there are, of course, multiple methods. I'm going to talk about the most important and most useful resources that, in my experience, you can use to learn. One particular, way that is at the center of the attention in research now is showing very promising results, is what is called deep reinforcement learning. That is something that basically combines deep learning and reinforcement learning together. The first milestone obtained in this domain has been with the deep QN, what is called deep QN. Here I put the reference on screen, and it was, this research dated 2014. I believe, they built a deep neural network able to receive as input the screen pixel and decide which will be the best next action. And so they trained the deep neural net to solve this problem on the Atari benchmark, so another video game based reinforcement learning task, multiple tasks, I should say. And yeah, this is the first, important result, combining deep learning for representation of features, so extracting features from screen, so control from pixel. This is how it is usually called. Using the pixels of the screen, you just extract features, and based on those features, you define your policy, selecting the best action that corresponds to that configuration of the environment. So even better now, one of the most important algorithms in the context of the deep RL is what is called under the family of policy gradient methods is called proximal policy optimization. This algorithm has been the one that allowed OpenAI to train OpenAI 5. That was their AI algorithm able to beat the world champions in the 5 versus 5 match in Dota 2. That was a great achievement because of many things. We will come back to this later. And so basically the idea is to build a deep neural net as the one that is shown here, and that we will be using, because the agents that I'm going to show you is using exactly PPO in a very similar fashion to the one used by OpenAI. Of course, on a problem that is way, on a different scale in terms of complexity, but still the approach is very similar. And as you can see, our network, and we will go into the details of it, is composed by a convolutional neural net that is extract features from frames, so from images, in parallel of a fully connected one that extract features from the additional information. Then these two family of features are concatenated together and provided as input to the final fully connected neural net that is in charge of selecting the action. So this is how our agent is featured, and we will see exactly what it has inside of these boxes. Now, there are a few interesting techniques that are pretty advanced in the context of reinforcement learning, and there are also, all those advanced features and techniques are all open, research problems. So there is a very huge amount of opportunities and possibilities to explore these fields. The first one is imitation learning. As the terms conveys, it's a domain in which you use human experts, usually demonstration, but not necessarily human, but in general expert demonstration of a good behavior, and you use those examples as inputs to your model. And so in order to show it how an optimal policy is behaves. So in the case of games, you can record yourself playing and provide those examples to your model, for example. In other contexts, you can use a standard control system. For example, for drones that fly, you can use a standard control, classical controller to bootstrap your model and start the learning with the reinforcement learning approach from there. So bootstrap your model, you get it started from a good point, having acquire some knowledge from the demonstration of a classical controller, and then from that point on you can just start learning in a different way. Self-play is another very cool advanced technique in this world, and the idea behind it is that you have a model, and instead of just training it with examples gathered from, for example, from experts, you let your model play against itself. And so by facing himself in a good apart from the fact that you are able to scale this approach way better than collecting demonstration from the world, because imagine you would you want to build a data set of your expert demonstration to be provided to your model. You need to record yourself playing, and this is of course time consuming and definitely not scalable. While with self-play, you are able to replicate your agent multiple times and run it in parallel, for example, with multiple instances, and we will see that later. And so you will be able to let your agent play against himself in parallel multiple times. And so this is a first very important positive aspect. And it is also coupled with the fact that your agent will be facing always an opponent of similar skill level. And this has been demonstrated that helps training. Now, another one is what is usually called human in the loop training. Human in the loop training is different than imitation learning. So in this case is we as humans, we are able to identify an optimal behavior, even if the reward function is not perfectly able to describe it. So for us, what I'm saying is, for us, it's simple to identify a promising behavior in an agent. It's not so simple to encode that in a function. And so by means of playing this role of judge, we are able to speed up training. Let me show you an example of it. Just give me a sec. I do have a video here. This is again from OpenAI. Now you will see here there are two hoppers. The goal of this robotic task is to make it learn to do a backflip. At the very beginning, they're doing random things, and there is a human that is pressing left is better or right is better. At the very beginning, is not clear which one is better than the other, but still you can have an intuition, and this is where we as humans play an important role. And just by telling the system which one is better, you at the end are able to obtain something like that is able to perform the whole the task, even if it was not super clear which one was actually better than the other at the very first stage. And so this is where human in the loop plays a role, speeding up training and avoiding the complexity of writing a perfect reward function. Okay, so yeah, these were three advanced topics, and yeah, to approach reinforcement learning. Now, moving on, let's talk about a little bit of challenges of reinforcement learning. First of all, the theory. As I said, you can see reinforcement learning in some sense as a generalization of the supervised one. Is a non-stationary problem because your target, your goal is always changing. You don't have a static data set. The theory behind it is pretty complex also. This is typically a challenge to approach reinforcement learning. Another one is what is usually called sample complexity. Now, here we come back to OpenAI 5, and the screenshot on the left is showing you a typical observation for that game. So for Dota 2, you have in control multiple bots, 5 bots. You have a complex environment, partially observable, so you cannot see the entire screen. I mean, the entire board. Your opponents are doing complex things, and so this is a very complex problem. And in order to deal with these problems, one of the major challenges in reinforcement learning we are facing is called sample complexity. And this means that you need to interact for a long time with the environment in order to obtain good results. You can imagine, it's similar to the need for a very huge amount of data for supervised learning if you want it to generalize properly and to perform in an accurate way. Now, for reinforcement learning, you need a very long interaction with your environment. And just to give you an idea, on the right, there is a table that is showing what OpenAI used to attain the results they achieved. So OpenAI 5, look at the rightmost column here. They have been training their model in 128,000 CPUs on Google Cloud. So 128,000 CPUs. And 256 GPUs again in Google Cloud Platform. So the experience they collected was in the ballpark of 180 years per day of experience. So it was like every day they train, it was like a common human playing for 180 years. So this gives you the idea of the problem of sample complexity. We as humans, we don't need this huge amount of experience to become good at this game. While reinforcement learning in its current configuration needs that. So this is what is called sample complexity. And this is the overview of their infrastructure. We again will come back to this one, but as I told you, in the upper part of the scheme, you will see there are one optimizer that is the GPU connected to the what they call rollout workers. So while in supervised learning, the bottleneck is typically in the GPU. In this case, in the case of reinforcement learning, it should be pretty clear from this scheme that the bottleneck is not there. It's on the collection, the experience collection. In fact, you can see here 500 CPUs are used per each GPU in order to collect samples of experience that are used to train the model in the GPU. Now, this is multiplied by 256 in the third dimension that you can see. So there are 256 GPUs, and for each of them, there are 500 CPUs. This is for training. And then at the bottom, you see there are what they call evaluation workers. So 2,500 CPUs dedicated only to evaluate the progress of training. Yeah, so this is when I refer to the sample complexity, this is the infrastructure needed. Now we will come back to this later when talking about the umbra. So now you can understand why the greatest part of reinforcement learning research and also application is done in virtual environments. So when you approach reinforcement learning, you will find yourself typically dealing with simulators or video games. Reason being, virtual environments are can be used in parallel. So you can parallelize executions and this is something that you cannot do in the real world, first of all. And so if you have a simulator of a vehicle or a robotic hand, in the virtual world, you can just replicate a very high number of instances of the same object easily. I mean, you just need compute. While in the real world, you should build, you should build the hand, as a hardware, or you should build Tesla vehicles for autonomous driving or drones. And this is, of course, way less scalable. And this is one reason. The other one is, as usual, these environments, so this approach, the reinforcement learning approach, starts with random policy. So you're starting when you don't bootstrap from expert demonstration, your starting position is your policy will be a random one. And so you will start gathering feedback from the environment in terms of reward by just pressing random buttons for a while. Well, doing that in the virtual worlds is okay. Is not okay doing that in the real world. So you can imagine like flying a drone randomly, controlling the thrusters or their motors for their blades in a random way. 100% you will crash, and this is of course a problem. So this is the other reason why typically virtual environments are the common natural set for reinforcement learning research and also industry applications. Yeah, moving to that, of course, as you can imagine, video games are a perfect setting to adopt these kind of solutions. For example, improving the gaming experience, building more intelligence, non-playing characters, populating online servers with good opponents, intelligent opponents, instead of just scripted bots. Other places, for example, trading, so using trading simulators to train reinforcement learning bots, trading bots, is also something that is happening. Using reinforcement learning to optimize advertising, it's also a thing. And there are also applications for robotics in the sense like of, for example, control of drones. And again, here a major role is played by simulators, but also bootstrapping their policies using classical methods. So you use classical methods, you make sure your policy, your deep reinforcement learning agent is able to replicate behavior described by classical control methods, and from that point on, you fine-tune your policy, being able to face conditions that can be worse than or more limited than the ones you are typically facing. For example, in presence of a failure of a sensor like an inertial measurement unit or a rotation sensor, you may still be able to obtain an optimal control method using DeepRL, because you can train that in simulation, faking, let's say, or simulating a failure, and still training your controller to behave appropriately. Now let's move to the final part of this reinforcement learning overview with resources. Now what I'm going to share now here is derived by my own experience, and I can tell you that following this path can give you a good understanding and also experience in reinforcement learning, and it's a good path to start from. First of all, environments. If you want to understand something, and this is true not only in RL, but in general machine learning, and even more generally in everything technical you want to study, you need to experiment what you learn. And this is one of the reasons why I wanted to also, I was attracted by RL, is that many times you can do that while still having fun. Because While in data science, and I love data science, I do it a lot also, but also, having to deal with CSV file is one thing when you keep looking at numbers rolling in your screen. Looking at video games being played by your agent and the reasoning on what can be improved is a way more fun way of experimenting. And so here I'm listing three options. Of course, there are way more than three options for reinforcement learning environments. And of course, one of the classic is OpenAI Gym on the left, Unity ML agents on the right. That is also another one that is very famous. And in the center, I'm listing our own suite, the DIAMBRA Arena. I will show it to you, and it will be the object of our let's say coding session later. And yeah, there are many valid reasons why you can find it easier to start from the umbra. So okay, these are three options for environments. Then you can definitely implement your own agent, your own algorithm, but as usual in the field, you should also keep in mind that you can rely on very cool and professional libraries that are already prepared for you, like those listed here. I don't know, and I'm not familiar with RL Coach on the right, but I know it's one of the references. What you will see later has been trained in stable baselines, the one on the left. Array, RLlib at the center is probably the most advanced one. They all feature the best algorithms you have. For example, Ray at the center is the one that allows you to, scale your training infrastructure very easily. So make use of multiple GPUs in parallel, even distributed in different machines. So it's a very professional one. Stable baselines can be maybe a little bit easier, and it's still very good. So yeah, these are options for you. And now moving to books and courses. Well, starting point, I can be pretty sure this is the best one for everyone. I mean, with no doubt, is Reinforcement Learning: An Introduction. Is by Sutton and Barto. This is seen as like the main reference text for reinforcement learning. Then I also listed something I've been working on the Reinforcement Learning Workshop by Pact. I co-authored there this book, 3 chapters in it. It's a very hand-on book. It's good. I mean, when I was writing it, I realized all the aspects, involved, and I believe it can give you a very good hands-on experience. Then lectures. I listed 2 of them here. I only attended one, that is the DeepRL Bootcamp by Berkeley. It's dated 2017. It's great. Now, it is focused on DeepRL, not reinforcement learning in general. On the right, you have reinforcement learning lecture series by DeepMind and UCL, so University College of London. And this is something I still haven't watched it, but I feel it covers more or less everything that is covered by the book in Sutton and Barto. It's so about, in general, reinforcement learning, not only DeepRL, while Berkeley is focused on DeepRL. These are, these things, all these resources can get you started very, in a very good way. After that, as in machine learning in general, you need to rely on papers, because this field is advancing so fast that you need to keep the pace with papers. And of course, open access like archive, conferences, and journals, all valid options, and you should keep an eye on everything. Finally, also film, and this is not a joke. I mean, if you haven't watched it, you go on. It's public on YouTube on DeepMind channel. You can go AlphaGo. You can go and see AlphaGo the movie. It's great. If you're able to at least have a grasp of what is happening behind the scenes by reading a little bit, even just the high-level surface of AlphaGo in the paper or in a blog post, You would even appreciate even more the film. Is just amazing. And so this is another cool thing to do when approaching this field. Yeah, so now we are moving to DIAMBRA. Let me share in a very few minutes, we're going to see an agent in, running. Let me just present you the project very quickly. You can think about it as composed by three components. The first one is the Umbra Arena. That is our RL environment package. You find it on GitHub and also on Docker. And it provides OpenAI Gym standard interface, Python interface for popular fighting games. And it is perfect to study and to start experimenting with RL. And so this is the first component of the Umbra. The second one is our RL community. We are, we believe that we need to grow together in RL, and so we do have our own Discord server as well as our Twitch channel and all our socials where we want to bring the community together. And the third one, in this regard, the third element will play a major role. We are developing and we will be soon publishing and deploying our AI tournaments platform. So it will be a web platform in which you will be able to submit your agent to compete against, either the computer itself or other agents submitted by other participants, other users. There will be competitions with prizes, and it will be super fun because you will be watching your agent playing against other agents. So it's kind of like robot wars for RL, deep RL agents. We already had our first AI tournament last year. It was also, with money prizes, 1,500 euros, sponsored by Reinforcement Learning Zurich on Dead or Alive. We will have way more than that in the coming months. So references about DIAMBRA, it's pretty easy. You can just go on the website, diambra.ai, and there on the top right, you will find all our main socials. From GitHub, you can access our DIAMBRA Arena package, and from that, our documentation, it's all super documented. We will be using it for coding, and it can, you can just go in the website and reach GitHub repository and finally the documentation there. We also, as I said, have a Discord server, our Twitch channel, so you can definitely follow us in all these channels for if you're interested in more of this. Why, and this is the final slide before moving to the agent, why I suggest you to start from the Umbra Arena. Well, first of all, all the reasons are listed here. First of all, we have cool environments. So our games, fighting games, are like Dead or Alive, Street Fighter 3, Ultimate Mortal Kombat, Tekken Tag Tournament, King of Fighter, Samurai Showdown, and we are working to add even more. And for now, we are focusing on retro games. So, and that's one thing, but we already have in our roadmap the move to modern games. And for now, we're focusing on fighting games, but soon we will have additional games like platform, like sports games. So we are already working on that one step at a time. Cool environments, sure. Tractable dimensionality. I trained the agent you will be watching has been trained in my own PC, even a low-level one. So we want to, we are building these environments so that everyone can use cool environments and train their own agents at home without the need of such a big infrastructure like the one OpenAI used. It's maintained and well documented. You have all the documentation with all the details you need. There is direct support available. You can join our server in Discord. There is a dedicated channel there, so to ask for support for problems you may have. It's available for Windows, Linux, and Mac, so it's definitely cross-platform. And there are advanced features available, like in that one, we already provide experience recording, imitation learning. You can implement human-in-the-loop training, self-play, so you are able to build, make your agent fight on both sides of the screen, so fighting against himself. So a lot many valid reasons to use DIAMBRA to experiment on these things. Okay, now let's move to the demonstration, live demonstration of the agent. We will be using a policy that is, as we already said, is linking frames and additional info to actions. So based on the frames we receive, we select the button to press. The architecture is the one you see here on screen, and I'm not sure, we can go to the details right now. So there is a convolutional neural net that is extracting information from frames, a fully connected extracting features from additional info, concatenating them together and passing them to the policy. And this is the architecture of it. So there is a 3 convolutional layer, a flattening, and a dense for the CNN at the top. There are 2 dense layers at the bottom with 64 hidden neurons. So for a total of 320 latent variables. Those latent variables are then passed into the final policy that has just a 1 dense layer, outputting 12 values for 12 actions, and then you select the one with the highest probability with the argmax. Okay, so this is the architecture. I'll talk about the training. I can talk about it just now, and then that's the last slide. So if you compare this slide with the one by OpenAI, you realize why the DIAMBRA Arena is made, for everyone. You can see here, I trained everything in a single workstation. I had 2 different workstations, so this is the most powerful one that is still pretty normal. The rollout workers, I used 16 different instances of the environments in parallel. I have so using 8 CPUs, each with 2 threads, so 16 threads, collecting experience. This experience is set to the single GPU I have, that is 1080 Ti, and I can assure you this is not the bottleneck. So you can even achieve good performances even with a minor slowdown, even using just CPU training. The duty cycle of my CPU in this configuration was about 30%. So it was working 30% of the time, because the bottleneck is in the rollout collection. So this is, again, a demonstration that these environments can be learned in every single PC. Now let's move to the demonstration. First of all, I will be executing a random agent playing Street Fighter. Okay, let me run this one. Then after watching the random agent, we will be running the trained one. And maybe at that time we can start taking questions, because hopefully the run will be long enough so that we can definitely start answering questions. Let's start with the random agent. Now, you may think that the random agent will be playing in a good way, because you will see he will be able to hit the opponent a few times, and maybe he could also win a round or even a stage. But keep in mind that our reward function is not related. Actually, it is related, but is not exactly the number of rounds you win. Is the health. So the score you will be seeing here is the one that we want to optimize. Now, again, this score is of course related with the number of rounds you win, but they are not the same thing. And just to confuse a little bit your ideas, in the condition in which you obtain the lowest possible reward is the one that makes you arrive to the end, to the final stage. Okay, now this may seem counterintuitive, but this is the case. If you want, we can talk about it more in the questions. But as you can see right now, our score is minus 0.75. Now the score is normalized so that if you win with a perfect, so your full health bar without losing any health, the total amount of reward you will collect is +2. So losing by a perfect means -2 for each round. In Street Fighter, you need to win 2 rounds. So a match that ends with 2 rounds lost by a perfect is a -4. Now you see we lost the first round of our random agent with the -1.7 that will be updated to minus something more, minus 1.73 at this point. Second round started. As you can see, sometimes we are able to, hit the opponent, but it's just, by pure chance. We are performing random actions, and you see them on the left in the screen. So we are just pressing around buttons in a very strange way. We will see after this. Now we are about to lose. I think we will lose in this stage, and we will compare this performance, the random agent, that is the starting point of our algorithm. We will see and compare this one with the trained one. Okay, and we will be able to make comparison, and we will see how far we will be able to arrive in this game. Now we are about to lose if everything goes as normal. And the final hit, yeah, that's it. So a total cumulative reward of -2.76. Now this is a little bit worse than standard, but still, in the same ballpark. Now let me run the trained agent, and let's see how it goes. I will start commenting a little bit for the first stage. There are 10 stages on this game, and hopefully we will reach the final one. So let me comment the first one. Then we can start taking questions if you want from the chat, and I will ask for Marco support for that, so that I don't need to keep an eye on the chat. The only thing, let me start with the basics. First of all, this trained agent has been trained with only Ryu. Okay, so of course there are multiple options you can use. You can decide to train your agent on all characters, to use all characters. You add that info to the things you keep in consideration when playing, of course. But all these things, they of course increase the size of the observation space. So this agent has been trained to use Ryu and only Ryu. Let's see how it goes. This is, as you will see, this is freezed a little bit just because it needed to load the weights. And then, as you can see, we are starting hitting the opponent pretty easily. And the first one is a perfect. So as I said, a perfect means 2.0, a total cumulative reward for the first round. This will be updated soon, as you can see, 2. Now, okay, we are starting the second round. Hopefully this should be pretty standard. I've been watching this agent on and on, as you can imagine, and not only on this game. But yeah, okay, so the first stage has been passed with almost 2 perfects, and we are moving to the second one. Now there are 10 different stages. Not everyone will be as easy as this one, because there are characters that are more complex to face. And especially the last one, we will talk about it. If you want, we can definitely start addressing questions if there are any. Otherwise, I can just keep commenting on that. I should say I'm not an expert of these games. Actually, this is also one good outcome of my interest in RL, because for me, I think it was easier to train a deeper RL agent to play for me than, with respect to what I needed to do to learn playing these games. And so, yeah, I cannot share much about the history of the game, specific features of these characters, but as you can see, there are multiple things that we can notice about our trained agent. For example, you see that we are, you will see, especially in the last stage, excuse me for a second, you will see in the last stage that the standard approach, so like being very aggressive, will be modified depending on the conditions of your health. So when you will have a low health value, Ryu will become more conservative, and so we'll start to avoid these approaches, very, very aggressive. and will be more conservative, defending himself and so on. But so this shows a very good way of adapting the behavior depending on the situation. And yeah, another thing that I can tell you is this agent is using 4 frames. I don't remember. I mean, I trained different versions of it. The biggest one was using 6 stacked frames. So the last 6 frames stacked in the 3rd directions, grayscaled, so not RGB, of sides 256 times 256, so in resolution, so shrinking them down. And has additional information. They are using previous actions, so the previous 12 actions, together with health values of both yourself as well as the opponent, and side, so on which side you are, if you're on the left or on the right of the screen. More or less that's it. So all these things are used to decide which action to take next. And this is what it takes, for the agent to learn this game, to play this game. Another peculiar aspect here is the fact that we are not using super moves, as you can see. We are using just punches and kicks, and a combination of them, and that's enough to complete the game. Now we are running the game with, in this case, with difficulty 6 out of 8 levels. Street Fighter has 8 levels of difficulty, but the same agent is able to complete the game, has been able to complete the game at the highest difficulty level. So even if it has been trained with the difficulty level 6, it was able to finish the game with difficulty 8. Yeah. So I don't even remember the stage we are, but I believe it's kind of like 5, something like that. So it's gonna be a while until we reach the final one. The second last is Ken. I'm not sure it's for Ryu only or in general the rule for this game, but still for Ryu, the second last stage is Ken, and the last stage is the final boss. That is a very complex one to face because it has some powerful super moves. One of which is called Resurrection. Oh god, this is a super move, but still, we were able to land a perfect anyway. Now, the final boss has this particular super move that is called Resurrection, and it works this way. If you beat him and he has the full bar, the bottom bar, that is the bar for power moves, full, he will recover the entire amount of health. And so it's like facing him twice for 2 rounds without recharging your health. And this is a very complex one to beat, to face. Now again, also Elena is that is this character, this opponent one is not easy to face. As you can see, we are about to lose a round now, and this is typical. As you can see, we are more conservative a little bit now. You see Ryu that is waiting for the opponent to approach. Oh, we are right there. Okay, that was good. But you saw that at least this gave us the opportunity to see the different approaches we are adopting. At first, with your health bar that is full, you go and you are usually more aggressive against your opponent, while when your health is low, Ryu is typically more conservative, waiting for the opponent to attack and adopting countermeasures. So this shows, I mean, I just plugged, I just plugged stable baselines. I engineered the architecture of the policy network, and then I tuned the hyperparameters manually, and that's it. So this is the power of RL. I mean, it is able to learn complex tasks without any, prior knowledge, without any specifications made by a human expert, just by interacting with the environment, starting from random behavior and then learning from the reward that is provided by the environment. So this is by far, recognizes a very, very super promising field and approach in the domain of machine learning, and we will be seeing it rising in the coming years. At least this is, oh God, this is at least, what the most important researchers and professionals think about this field. Okay. So I'm not sure if I had to check the chat for questions, or let's see if I'm able to. Okay, yeah, I'm able to open. So I encourage any one of you, if you want, if you have questions, any type, from resources to anything you may be interested in, feel free to ask. I'm more than happy to answer. So let's see. I don't remember what was the stage now, but we should be pretty close to the end. If not the 7th or the 8th, this one should be more or less it. Let's see if today it's a good day. I've been presenting these agents. I've been running them on Twitch for a while now, and I'm usually landing the final stage. It's pretty common. Then finishing the game is not simple. Thank you, Aurelio, for your question. So you're asking how long did it take to train the agent? In this case, okay, so as I said, I experimented with different combinations. So I'm not sure this is the one that provides you the fastest possible training time. But you can think, again, I've been using a very basic computer for this. Oh, this is the second last stage. Okay, we'll see. So a very basic PC with a 1050, 4 gigabytes of RAM, and i5, a very basic CPU, not so powerful. And with that, it took this agent can be trained in about, let's say, 2-3 weeks with such a very bad computer. So with just a slightly better one, you can give that, you can go down to 3 days, about 3 days maybe, or maximum a week, more or less. It really depends on the hardware you have, but still, that's the order of magnitude in general. Yeah, so let's see. We won the first round, and so this is the second last. Thank you, Aurelio, for the question. Okay, let's see. Can is not easy, guys. It's one of the best of this game, but as you can see, we were able to land to the final stage. Okay, now we'll face the final boss, that is Gil, and it will be not easy to beat him, but we'll see. And every time is not easy. Okay, so thank you, Azad, for the question. I'm gonna answer it right. Let's focus a little bit on this, and then I'm gonna answer it. So the agent has been trained. I will start answering, and we'll see. Has been trained using, competing against the computers. So I believe that for the mechanics of the game, the only characters he have not faced is the Ryu itself, because when you select Ryu, you don't fight against him in the standard game mechanics. Okay, so the run, the arcade doesn't propose you Ryu as an opponent. Now, about the generalization, that's an important question. So you see, take a look at the resurrection. This is the problem. We beat him, but he was able to recharge the full health bar because of the resurrection move, and this is why it's super complex to beat Gil. But still, I know, there are videos online. You can watch them. We were able to beat him, and as you can see now that we have a very low health bar, we are performing a very defensive move, like keeping, most of the times remaining at our own corner, waiting for him to approach, and trying to, face him in that way. Let's see. This would be great if we are able to beat him while after a resurrection. Let's see. Yes, a very good one. So you see, I mean, everything has been learned by himself. I never added any prior knowledge. So about generalization, well, the most is a tricky one and is very important. On one side, the generalization is assured by avoiding training too much, otherwise you would be overfitting. And on the other side, the randomness of the game itself assures you won't face all over and over the same condition. And so in some sense, every new run is kind of a more generic one. But let's say that the typical way in which you approach generalization verification in this case, and in these games, is by modifying. Oh, this is a super move, and we lost it with a super move. That was pretty close. It's by means of the difficulty level. So if you train your agent with a very low difficulty level, or let's say not low, but let's say a medium one, and if you evaluate that with a very high difficulty level, that is something that changes a lot the mechanics, and it's something that you can use to measure how good you are generalizing your own knowledge. Now, of course, there is another thing, and this is also another cool thing about the Umbra. Okay, this is another resurrection, but we are approaching him trying to avoid that. Okay, not good. And it's a particular features provided by the Umbra. So we, as I said, oh God, we're about to lose. I'm sorry about it, but still. Oh, stun, come on. No, okay, this is definitely something that we didn't learn. So to approach when they are stunned. No, too bad. Anyway, yeah, we were not able to complete the game, but still, take a look at the score, 25.4. If compared with the first one, it's pretty clear that, with the random agent, it's pretty clear that we were able to, improve a lot. Now, okay, coming back, let me stop this. We do have other potential episodes, but I won't go there. Now, coming back to the generalization question, we are providing, and now we will be taking a look at. This is the GitHub repo, and from the website you can just go on the top bar. You can approach that. We provide different games, 6 different games at the moment. More, there is a 7th one already ready, and we are working on a 8, and we will continue. They are all fighting games. So the Umbra is the perfect setting to explore generalization on different tasks, because in general, they are all fighting games. And so you can definitely measure generalization capabilities by using by training an agent on a game, maybe 2 games, and then deploying it on a 3rd one. This is something I didn't try for now, but it's one of the major, interests of the community. Having a good set of similar tasks that allows you to measure generalization capability. So together with the game itself, together with the difficulty levels, this is another way in which you are able to measure generalization. Yeah, so I believe anyone who has additional questions, please, do not hesitate. Oh, nice one by Roberto. Thank you, Azad, for the question. That was really interesting. And I see you worked in RL because of that question. Thank you for the question, Roberto, about testing different methods. It's very interesting. And I should say that at the moment, I only tested PPO extensively. I didn't use off-policy methods like Q-learning or similar ones. Mainly because of the time. As you can imagine, we are working on these games, and we need to make sure they are all learnable and they are free from bugs. So I need to train agents that are able to complete the game, or at least to reach the final stages. And once I do that, I need to move to the next game. But of course, as I said, okay, maybe this is a good moment to show this slide. Of course, we are more than happy to collaborate with anyone interested in it. For now, we are just a bunch of guys working on this project with good hopes for the future, but there is not a company behind it. So all collaborations are, for the moment, volunteering collaborations. Still, we're already been working with people from industry as well as from universities, and a very good approach for example, for a thesis could be to measure different performances that are achievable by different methods. And so this is for your question, Roberto. I don't have any comparison yet, but it's something that is for sure interesting, and we would be super interested in supporting anyone wanting to do that. Yeah. So moving towards the coding session, as I said, this is the GitHub repository. You can easily find it in our website. And with that, there is also a documentation. You can reach the documentation here. Let's open it in a different, here. So the documentation provides all the guidance you may need to from installation to debug, to most advanced features. The GitHub repository provides also examples. We will go through that. Now let me get started from the installation. As I said, we provide we support many different OSs, Windows, Linux, and Mac. The native GitHub repo can be installed on Ubuntu and so on Linux, and in both Ubuntu 18 or higher and Mint 19 or higher. So it's Debian based, Ubuntu and or Mint. And if you have those, you can just clone the repository. First, run the setup.os.sh, and secondly, just pip install dot from inside the repository, and that's it. It installs the DIAMBRA Arena, and it's all explained in the installation page. If you go in the installation, you select which is your preferred solution. In Linux source, you have just all the steps listed here. If you prefer to use Docker, either on Linux or Windows or Mac, all the details are here again. You just pull our Docker image and you are ready to go. With Docker image, you can execute that in both with the GUI or without it. So in order to speed up execution, you can just get rid of the UI, and then in the evaluation phase, if you want to take a look at how your agent is behaving, you can do that. You can use it. Installation takes just a few minutes using Docker in all the environments. The only thing that you need to do after installing it, you need to retrieve games ROMs. Our own environment is just let's say an interface to a very common emulator. So we are providing this interface. We cannot provide games. You need to own them in order to have those ROMs from a legal point of view. This is true in many countries, not in all. Actually, there are multiple countries where this is not a problem. And yeah, you can obtain them pretty easily. And when you place them in a dedicated directory, you just provide that directory as a setting and everything is good to go. After that, after installation, a very basic usage is what I already showed you. And so the gist we were watching before, it's it. It's very simple, few lines to run the environment. and both with and without the help of a launcher, because if you're using Docker, you need a launcher. Actually, we provide a launcher to make your life easier, but you can, if you're familiar with Docker, you can just work with that, and it's pretty easy to. Everything is in the documentation. Now, before moving to the code, all examples that we provide in the GitHub repository are listed here. So single player environment, for example, and there is an example, and this will be the one that we will be using in a moment. Then there are multiplayer environments, so playing in a two-player games. What wrappers options, because you may need to wrap your environments inside some interfaces to shrink your image, to normalize it, and all these things. We provide multiple wrappers already, and so you can definitely use them. And there is this example that is showing you what this wrapper do. Then there is human experience recorder. This example allow you to let me go. Maybe this is useful. This allows you to record your experience as a gamer, so you can just link a gamepad, and you should be able to configure it properly. So something like this one. And after having it configured, you can just attach it. And as you can see here, we provide our own interface to the gamepad, and you can collect actions from it, send them to the environment, and then record them. And finally, this recorded experience can be used for imitation learning, so to load them and use it for training, a model. In the documentation, you find all the description of all the environments, like a very general overview of how it works, settings, and then for each environment, like a description of, for example, all the details of the environment, like how many actions it has, the resolution of the screen, the difficulty levels it features, number of characters it has, different action spaces, a representation of the observation space, and then all the details you need to train these environments. The wrapper section in the documentation provides you with an overview of all the wrappers we have, and you can just directly leverage. For example, there are wrappers to shrink the image down to the size you want, to make it grayscale, to stack actions together, to stack frames together, to scale things around, and so on and so forth. There are also utils and details on imitation learning. So all you need, you can find it here, and we will keep it up to date while we add the new environments and while we add new features. So let's very easily move to the example. Now, this is my terminal. I'm in Ubuntu, and so I will be using, actually in Mint, I will be using that. This is, the folder you see here, this is the repository. Okay, what you find here inside is the repository of the DIAMBRA Arena. And as you can see, there is the example folder. In the example folder, you have launchers for Docker. In our case, we don't need that. And then there are multiple examples in the form of Python scripts. Let's take a look at the single player one. Okay, so step by step, it's pretty easy. Let's get rid of the options, the parse arguments. Okay, this is just to handle arguments you submit from the command line. First of all, we need to build the settings dictionary. The setting dictionary is something that provides settings to the environment. And there are just two mandatory requirements. The first one is you need to specify the game you want. And you can retrieve the game code from the documentation. So each game, for example, if you go here, environments, game, and specifics, for example, Dead or Alive, the game ID is Dead or Alive++. Tekken Tag Tournament, the specifier is Tekken Tag T. So Tag T. So in this case, if we want to take a look at Tekken, This is what we need to provide. Settings, now ROM's path. And this is something we need to provide the environment. And this is where we stored our own ROMs files for the games. Then settings, additional settings start. There are, for some systems, they are just default values, and complete descriptions can be found. Complete description can be found in the documentation. So we have a very high level of flexibility here. For example, with a keyword player, we can select if we want to play on player 1 side, on player 2 side, so on the left or on the right. If we want it to be random, so randomly selecting player left or right, this is what I used, for example, for training. And with P1, P2 together, string together, you can use a that's the 2-player game. Render, okay, this is pretty easy. If you want to render the environment or not. Lock FPS, these games are supposed to run at 60 FPS. If you use false, they will become super speed, they will be speed up. So you will be seeing them running very fast, usually. And this is what you should use for training. Now, if to activate sound, minor thing, step ratio, you just don't think about it. And then headless too is if you want to run it headless, like for example, server side. Additional thing, continue game. Like when you lose 2 rounds on the same stage, if you want, you can prescribe the system to restart, to continue, like when you insert a new coin. And this can be prescribed by via this keyword. You can use a fixed number of continues, and this is minus something. It will create an integer from this, and then that number will be the number of continues you will be pressing. Otherwise, you can also prescribe a probability of a continue, so like 50%. So 0.5 would mean 50% of the time you will continue, while the other 50% you won't. Setting the difficulty, it's here with a keyword dedicated to it. Difficulty. Characters allows you to select which characters you want to use. For example, in this case, I'm selecting a random character. Okay. Character outfit. The number of all these games, depending on how you select your character, they change the outfit. And so here you can prescribe. All these things are documented in the documentation, so you can just read it from there. And by prescribing 2 here, I'm telling the system I want a random selection between the first 2 outfits. Action space is discrete in this case, and attack buttons combination is true, and that's it. So with those settings, the most long part of the code is setting properly all these aspects for the environment. Then you create the environment with make, and then you just reset the observation, select a random actions in this case, send it to the environment, and just keep that until the done condition is met. Let's see if we are able to run second tag. Now this is the code, and I can just pretty easily run a single player environment. Okay, well, first of all, I need to activate my virtual environment. Yeah, I should spell it correctly. That's it. And because I'm using Conda as a virtual environment manager in order to isolate my environment, and having done that, single player is just run this way. I think I need to specify the wrong spot because it should be, let me see, it should be a required argument in this case. No, it's false. So I'm not sure. Yeah, okay, that should work anyway without the wrong spot, because I think I have an environment variable to handle that. Let's see it right away. I specified these are tricks that are also listed in the documentation. If you want to avoid specifying every time ROM's path, you can just add it to your environment variables, and this is it. So the umbra rounds path, this one is enough to get things started in that regard, and this should be it. Okay, so yeah, as you can see now, Tekken is running, and it will select. You will see a log file here. Sorry, a log screen. It will select random characters. And yeah, I will print out things like this to keep you informed. Difficulty level is 3. That is pretty low for Tekken, but sure, because in Tekken there are 9 different levels. And we are using Panda and True Ogre in the case of Tekken. It's a random choice that changes every time. Now, of course, okay, Panda became Kuma, but that's it, because the outfits, Kuma and Panda, are the same character. Okay, now you see this is a feature that we are providing. We have what we call an observation scoping. So we are able to advance when we want, in order to keep an eye on all observations that are printed in the log file and on the screen console, and advance with this frame. This is the frame we are receiving from the environment, and these are the observations. As you can see, now, for example, let's take a look at the observation we are receiving. So first of all, we have a frame. The shape is 240 times 512. The stage is the first stage. Oh, just a sec. Let's keep this on top. And yeah, so our own, for example, for Tekken, all these things are specified in the documentation. Our own active character is the first one, so 0 index 0, because we are using Kuma. That is the first one we selected. Now, if we will call in True Ogre, because is in the background in Tekken, okay, you see True Ogre. Now our own active char is 1. So this is telling us we are using the second character we selected. And so there are other things like bar status, the character that we are using, our own health, side we are on the left, so it's 0, opponent side is 1, the last action we performed, and so on and so forth. So this is the observation scoping. I need to keep the bar pressed here in order to make it advance. And you can, this is very useful for debug. So we are providing also this inside the repository, so you can definitely make use of that. And this is it. So this is for Tekken. And let's see. I can also. Okay, now the Jack Z is in the other one. So yeah, this goes on and on. It's a random agent in this case. Okay, so and we are facing a very low level opponent, because its difficulty is just 3 in this case. And so it's, as you can see, the random agent is almost able to complete and win. Yeah, win the round. So yeah, we're moving to the second stage. Anyway, we can just stop this one, and let's try to use another game. Not another game, but another configuration. And yeah, this is the multiplayer. So player 1 and player 2, and here we will be using 2 players. Okay, let me do the following. I won't stop the execution, and yeah, let's see if this goes well. Multiplayer, let's execute that. Now this will be executing Tekken Tag, and in a 2-player mode. So we will be using both first and second player, so player 1 and player 2, with random characters. Again, as you can see, this is a 2-player environment as specified here. And we are prescribing random characters, and player 1 will be using Bike and Michelle, and the second will be using Lei and Yoshimitsu. So let's see. So you see here, we are selecting what we prescribed: Bike and Michelle, Lei and Yoshimitsu, and then the game will start. Now, okay, Again, I think we will be okay. This is going by itself. Again, printing things on screen, and yeah, everything is going with random actions selected. Okay, so this is for Tekken. Yeah, I think that the most important part is this, because after that, the next step would be, when you have this running in your system, you just need to plug in one of the of your libraries, your selected libraries for reinforcement learning, and start training. It's pretty straightforward. Our standard interface is allowing you to do that pretty easily, because all reinforcement learning libraries are used to the OpenAI Gym interface. So it shouldn't be such a big problem interfacing that. Of course, architecturing the neural nets and finding the right number of, the right hyperparameters configuration. We plan to do some tutorials about it, but we're now focused on building the platform. So it's pretty time consuming, and keep in mind that we all have our full-time job for now, so it's not so easy to find the right amount of time, even though it's pretty exciting. So yeah, so this is where we are at the moment. As I said, we already have multiple games in work in progress, and we are also about to move on to the modern games. And this is something I really need to restrain myself from doing that, because I know that if I just start coding that, I can just become addicted. It will happen. I mean, even in case I will be needing to do that all by myself, but I will do that because playing with these games in RL is great. It's has given me a lot of satisfaction, because you learn very a lot of things. But using modern games is gonna be even better. But also, even not modern, it's still old, let's say, games, but in different contexts. For example, sports or platform games like Metal Slug or something like that. So it's gonna be really interesting, and also challenging. So where you learn stuff. I think this is more or less it from what I wanted to show you. Also, because I spoke for 1 hour and 40 minutes, and but again, also for that aspect, for the coding aspect, the very brief overview, you can find everything online. You have all those examples already ready on the repository. If you have questions, I'm here, so we can start answering also them. Otherwise, this is more or less all I wanted to share with you all. And so, Marco, I also ask you if you wanted to say something, you want to intervene, or you need to tell something about even logistics about this. I can definitely share these slides. You already have it. You already have the archive with them. So if interesting for someone, you can definitely share them with those slides with the entire audience, at least for having those resources listed down, so that everyone can just go around and take a look at those things. And of course, I would be super happy to both be connected with you, or with all of you interested in these fields, on LinkedIn, and have you on board on our Discord server in DIAMBRA, and also join our platform there. Because right now you can, in order to use these environments, you just need to go on diambra.ai and join us. You need to register here. You will be given a set of credentials, and you are going to use them to log in into the platform when using it.